Well, let's move on to the last talk by Dave Winningham. ISIS-1 and 2 observations of the plasmasphere, plasma sheet, outer zone interface.
I'd like to report coordinated observations from the ISIS-2 topside satellite, topside observatory, rather. Obviously it's topside, as far as satellite is concerned. I'd like to start out with the first slide. If you got I'm not quite sure whether this is going to be visible in these strong lights. Or am I just sitting here at the... It's the first slide is on. That's right. Okay, I was at the wrong angle. I can't see it. Okay, to start to give a global perspective, I'll use the data from Cliff Anger's Aurora scanner. In this case, it's the 5577 emissions. The reason for the skew of the horizon over here is the fact he's tried to overize the emissions just by starting the scan from the horizon at different times on the plotter. The white area in this region is sunlight scattering into the baffle. Coming out of the sunlight scattering, baffle scattering, you can see 5577 diffuse emission coming around, evening being over here, noon here, morning, and midnight approximately this region. So you can follow the diffuse aurora from the day side through afternoon, through midnight, and it crosses the horizon. You can just see just a bit over the horizon on the morning side here. It's blurred out in this picture, but in a later drawings I'll show that there is a weak diffuse arc in this region, and the satellite just passes a bit to the side of this weak arc. Next slide. Focus. Okay, this is just another version of spectrograms. The invariant latitude is running to the right-hand side, increasing invariant latitude. The pitch angle, don't worry about this, as they've got the targeting calls on maneuvering the spacecraft attitude. Coming out of the polar cap, you can see the weak polar range, which is moving up and down in energy due to the effect of the magnetic field, the changing V cross B. Coming in, we see a very sharp increase in the energy flux, a very sharp increase in the number flux. As we go equatorward, you can see that it's a very soft flux here. The average energy is running somewhere around 40 or 50 eV. To put this in perspective magnetically, this is in between a substorm which had its main phase around 2:30 on this date, which is December the 9th of 1971. And as we go equatorward, the spectrum stays relatively soft, but begins to harden. You see the average energy pick up. Energy is appearing in higher and higher, counts appearing in higher and higher energies. As we go equatorward, the fluxes both get harder and more intense. You can see the blackening in the spectrogram. We reach a maximum region of isotropy around, in this case, around 69 degrees. As we go further equatorward, you can notice a loss cone developing here. 180 degrees being upcoming particles, 0 degrees being downcoming particles. You see the anisotropy develop, appearing first at the highest energies, progressing to lower and lower energies until finally the spectrum softens away on the equatorward edge. The spotty counts in this area are due to penetrating outer Van Allen protons. Just barely visible in this case, it shows up more. In others, there's a weak trapped flux of outer zone electrons here, and a lower energy electrons here, photoelectrons from the conjugate hemisphere. This is a very bad slide to show these trapped outer zone electrons. Notice that this is a near midnight pass, about 2300 hours magnetic local time. The next slide shows the proton data for the same pass. It's on this side coming out of the polar cap, which occurs over here due to a shift in the times the proton side was turned on. You see weak fluxes of protons evidenced by the spin modulation here. They're being isotropic, looking at the number flux. A very empty loss cone actually going. There should be another 2 scales on here to show this up. Again, we see a hardening of the proton spectrum, coming very hard, actually going off the top of our energy scan, which is at 15 kilovolts, being isotropic throughout this whole region. We reach around 68 degrees, you see a rapid change in the pitch angle distribution to anisotropic. It's best shown in the number flux and the energy flux here, developing a twice per spin modulation. The protons are very weak, going here, that you can just barely see it in the number flux. they go down to around 66 degrees, or about a degree of invariant latitude equatorward of the electron fluxes. This is fairly typical for the pre-midnight hours. Again, penetrating outer Van Allen protons in this region. Okay, now I've shown this is what I could say is a typical profile, but in between substorm phases, there's another substorm that happens about 3 hours after this at 9 o'clock or 9:50 Universal Time on December the 9th. Next slide. Okay, I've taken the optical emissions from all three channels on the ISIS imaging system, namely the 5577, 3914, and 6300, and done ISO intensity plots. You can see, okay, this is now in a geographic latitude-longitude projection of the optical emissions. You can see, again, the shaded area corresponds to the baffle scattering in the instrument, baffle scattering of sunlight. You see the 1 kiloradian contour coming close to the cleft here, around through the night side, over towards morning hours, closing the contour here. Then an intensity maximum of about 1.5 to 2.5 kiloradians in the 5577 angstrom emission. Plotted on this is the projection of the ISIS-2 orbit down to 100 kilometers, and the dotted region corresponds to a region where we see precipitating particles of energies from 1 to 7 keV. I'll show in a later slide, 3 slides on, the satellite track across this. You can see this in better detail, how the optical emissions and the particle fluxes coincide very nicely. Next slide. The next slide shows the 3914 data. Again, you can see the 3914 contour at 100 radius appearing in the day side, going around across the horizon. Other contours, 300 radius and 1 kiloradian. Now, again, I've plotted the 1 to 7 kilovolt fluxes, the dotted region here. You can see, again, they pretty well span the region of intense 3914 emissions. In the next slide, I've mapped the 6300 data. It's a bit more mucky than the other two emissions due to the air glow. But we can see, again, the baffle scattering in this region. The baffle, you'll notice the baffle scattering is different because it's a different instrument on the other end of the spacecraft, so the scattering is different. The 2 kiloradian contour here is the cleft coming out of sunlight here, coming out of baffle scattering. 1 kiloradian contour going around through midnight, away to the morning horizon. 300 radian contour, and the intensity maximum here at 1.5 to 2.5 kiloradians corresponds to that weak arc seen in the simulated topside picture, or topside all-sky picture. The other intensity maximum corresponds to the maximum in the electron flux. I've broken this region into two different, into the energy band from 10 to 700 eV into two energy flux regions. The first one is less than 10 to the minus 2 ergs per centimeter squared per sterane per second. The second is greater than 10 to the minus 2 ergs per centimeter squared per sterane per second. The first lower energy flux region is on the poleward side where the emissions are low. As we go equatorward, go through the intensity maximum, you can see that we're in the larger energy flux region. In the next slide, I've taken the optical emissions along the magnetic subsatellite point and the particle fluxes that we observe. The particle fluxes in the top panel, again broken into two energy ranges from 1 to 7 keV, from 10 eV to 700 eV. The reason I've broken them up like this is to try to break them up into F region energy deposition and E region energy deposition, or above F2 max and below F2 max. The higher energy fluxes are the circles. You can see it's a very steep increase up to a maximum, a drop, a little bump, which is in the doesn't show up in the optical data, then a very sharp decrease. The lower energy fluxes, 10 to 700 eV, reaching a maximum slightly poleward of the high energy, dropping down, having a plateau, then dropping sharply. Okay, if you look at the 6300 angstrom data, which should correlate fairly well with the lower energy particles, we see the which is a square. So 6300 angstrom rises, and notice that it rises equatorward of the 5577 and 3914. 3914 showing it very sharply here, and the 5577, which has a higher background, increasing poleward of the 6300. You'll notice that the 3914 peaks very strongly in the region of the higher energy electrons, namely the 1 to 7 keV. The 6300 angstroms going much poleward, corresponding to the region of softer electron precipitation without any corresponding higher energy electrons. Okay, to try to show the ionospheric effects of the incoming particle fluxes, this now actually is going all the way from the day side on this side to the night side over here. The top panel is the vertical range from the satellite of oblique echoes seen on the topside sounder, or in essence sort of a topside backscatter radar. We've plotted the apparent range from the satellite here. The apparent range is 2500, 2000, and time across here. You can see the echoes, the satellite approaching the cleft in this case, entering the region of severe spread F, as evidenced by frequency spread on the sounder traces going up, down up to about 4 megahertz, crossing into the polar cap. As we approach the night side region, which I showed you before, as we approach the particle fluxes, you see echoes off the poleward edge of the low altitude plasma sheet, crossing through the low altitude plasma sheet region of less than 800 eV and greater than 1.5 keV electrons, then exiting out on the night side. And then here long range echoes which refract through the ionosphere and go out to as far as 3,000 kilometers. The other effect seen is in the region of the plasma sheet, low altitude plasma sheet, and in the region of the cleft, you see very strong irregularities in Larry Brace's Langmuir probe. These are now delta and absolute variations, not relative variations, and they're the ones that correspond to the refracting the waves from the equatorward edge of these particle flux regions. In the last slide, I just wanted to show for perspective to try to relate to the plasmasphere and magnetosphere focus is the electron density at the satellite altitude. You can see the very sharp increase in electron density at the satellite altitude in the region of the dayside cleft, going down, presumably convection, taking it poleward of the cleft, a very deep polar cap. This corresponds to the region of soft precipitation. In the region of harder precipitation, the scale height goes down. In the soft equatorward edge, again, the scale height goes up. We drop into the trough, and then you see the characteristic increase in the density. Regretfully, to get good optical data means that you don't get very good trap data or ion mass spectrometer data, so there's no way to tell where the O plus H plus crossover is in this pass. One thing I didn't show in one of the previous slides is sitting at 55 degrees, there's a sharp increase to about 50 Rayleighs, or 6,300 angstrom emission, which is extended in longitude and is presumably a SAR arc. Thank you.
David,
excuse me, I had one other thing. You want to go ahead, Rick? Where are you?
I'm ready.
Okay.
I just wanted to ask you.
Angus,
Yeah. No, I just wanted to ask you if you are able to try to do direct correlations between, say, the plasma pause as measured by Larry Brace and your lower latitude plasma sheet measurements.
Well, the answer is yes. They're on the same satellite. Have we done a lot of them? The answer is no. But the ones I have done, there's not. You know, they follow all the same problems that they have before, namely you get sharp ones, you get steep ones. And the best hope is to do a study with John Hopkins IMS and look for the crossovers and see the difference between the inner and outer plasmasphere. Do you want to do Cleft data now? Okay.
Okay, well that closes out this session.